Welcome to the 2021 Land Lab lecture series. I'm leading an inaugural studio this spring that frames a UVA satellite site, Milton Airfield, as a mesocosm for ways of knowing through situated making, where students are researching, designing, and eventually building a mesocosm investigation to then challenge, interrogate, and potentially reorient through a series of exercises that explore alternative ways of knowing and creating knowledge. And so in tandem to this studio, this lecture series is a parallel effort in positioning the studio's efforts on site within a history of precedents in theory and practice. And today we're joined by Katie MacDonald and Kyle Schumann, our, I think, first and only architects of the panel. They're assistant professors of architecture here at UVA and co-founders of After Architecture, a practice named to convey the built environment's impact on cultures and ecologies. Previously, they jointly held the 2019-2020 Tennessee Architecture Fellowship at the University of Tennessee. The research critiques conventional building practices, which face new life cycle questions and overextended supply chains amid the current environmental crisis. Such work explores how technological agency can help reconcile the intentions of the designer with the irregularity of natural materials and processes, leveraging data and feedback to reframe authorship. Recent projects include an installation at the Oslo Architecture Triennale in 2019 and a pavilion at the Knoxville Museum of Art. So please join me in welcoming Katie and Kyle.
Great.
I also need to make you guys co-hosts so you can take over the screen. Okay, should be good.
Perfect. Great, thank you. Thank you, Matthew, for the introduction and invitation. Your framing of Milton as a mesocosm resonates with our own interest in linking the field to the lab and finally, in our case, to the construction site. So we are excited to take part in this dialogue.
Can everybody see our screen? Awesome, great.
Entitled Growing Building, our talk today traces changing relationships between man and natural systems, at times growing together, at times apart. We will consider building as an act and mediator between the two. The talk is broken down into three sections: embodied intelligence, human intelligence, and biological agency. In the final category, we will put forth a series of experiments.
So to start out the first part of our talk on embodied intelligence, we're going to open with some work that is definitely not ours, but is of great interest to us. And that is the work of this figure, Ötzi the Iceman. And so here we have an object that at first glance is nothing more than the skinned paper-like bark of a birch tree. It's in fact an object designed and constructed in the Copper Age over 5,300 years ago, placing it 1,000 years before Stonehenge and about 900 years before the construction of the pyramids at Giza. The birch bark basket was discovered fairly recently in 1991 on the body of an individual now known as Ötzi the Iceman on the top of a mountain in the Ötztal Valley Alps on the modern day border of Austria and Italy. And interestingly, there's a kind of dispute initially over which country owned this archaeological find due to the way that the border is defined with the kind of shifting ridge lines of the mountains. So this figure, Ötzi, lived and died around 3400 BCE. And his bodies and belongings were preserved in the ice before a pair of mountaineers happened upon the thawing body over 5 millennia later. And so these are human artifacts that leverage the performative qualities of raw material, recognizing their embodied intelligence. And if we look more closely at this object and kind of look at how the form of these materials, being grown materials, are kind of used intelligently in a performative object, we find that this object has a volume formed or a shell by the birch bark. The circular form recalls the kind of nature of that bark and the growing of the tree, and its kind of restrictions in being able to be bent into certain shapes in certain directions. And found within this object was a sort of lining of charred maple leaves and charcoal fragments. And so it's thought that this was actually a device used to carry burning embers on these sort of high altitude hikes through the Alps, and was a way of kind of harnessing that power of fire and transporting that on one's person through the use of this vessel designed and constructed of natural materials. Along with this object were a whole series of other sort of amazing objects, each of which could certainly be a lecture in its own right. But we see from the bow on the left that was under fabrication in progress in the current state in which it was found, to the axe in the center that utilizes this sort of notch in the tree, to the clothes and footwear on the right that used grasses kind of woven and made into different sort of surfaces and forms that conform to the body. And so we're interested in every case here, how the sort of intelligence of this material contributes to the performance and function of the objects that are created by humans.
And so from this, we shift to the more recent, perhaps more destructive or fundamentally world altering example of human intelligence. That is the kind of human systems, human labor, human economies, human orders that take a central position in standardization. So we'll begin by considering a question central to modes of construction since industrialization, which is, how does one straighten a log? Since industrialization, the answer has been nearly universal across societies, geographies, and the answer has been to subtract, to transform the raw arcing forms of trunks and branches, which balance their search for light, water, and structural integrity into a simple orthogonal prism. In its earliest days, the Industrial Revolution birthed standards because mass production demanded uniform modes of manufacture regardless of geography. American construction embraced such modes for their ease, speed, and cheapness, and there is perhaps no building product quite so easy and cheap as the humble 2x4, which expanded to encompass an entire range of sequential construction practices and building products. This standard technology drove the housing boom in the early 20th century, championed by purveyors of prefab housing, who dressed this new technology in historic clothing in the form of previous architectural styles and floor plans, enabling widespread acceptance and adoption by the general public. Beyond industry, standardization practices were embraced by modern architects. In 1931, The Dwelling of Our Time, an exhibition by Lily Reich and Mies van der Rohe, displayed full-scale prototype homes surrounded by the standard materials from which they were constructed, a blatant association between modern design and these materials. The tectonics of the more recent digital turn extend the tendency to subtract custom form from standardized materials. Laser cutting, CNC milling, and water jetting privilege the subtraction of parts from sheet materials. More favorable, in our opinion, is the approach to straightening a log taken by Alan Wexler in his piece Reframing Nature, in which small incisions are made into the wandering trunk of a tree and wedges are slipped into the mass, redirecting the center line of the tree into a straight path. This additive operation maintains the trunk's taper, its protective skin, its efficient surface area. Wexler's log, leveraging the embodied intelligence of the tree, suggests another question entirely: why straighten, which is to say, standardize the log?
Our approach is situated between the totalizing digital world and the unfolding effects of climate change. If the gravity of the current climate crisis is indebted to mankind's historic tendency of superseding the needs of other organisms, conceptions of design authorship in architecture and beyond likewise center on the primacy of humanity, or have historically. We propose a conceptual shift from the authority of the human designer to a discursive and systemic relationship between design intent and ecology that can be enabled or mediated by technology. The recent maturing and increasing economy of technological advances, such as 3D scanning and imaging, tomography, thermography, evolutionary solvers, and parametric modeling, make data and feedback accessible tools in this collaboration far beyond the traditional sort of what we would call now maybe traditional digital fabrication techniques. And this enables a kind of kit bashing of technology in which processes are co-opted and aggregated. This field of inquiry is not without precedent. Marc-Antoine Laget argued for an elemental basis for architecture in his discussion of the primitive hut, while Sir Bannister Fletcher catalogs the most primitive forms of biomaterial architectures in his classic textbook, A History of Architecture. I'm sure everybody here is familiar with the work of land artists such as Andy Goldsworthy. And this work in particular identifies and reveals ordering systems within nature. And I think we could reevaluate a lot of this work and actually define it along kind of algorithmic or computational parameters in which the sort of qualities of each piece of material are carefully evaluated and then placed in relationship to an idea about a constructed or unified whole. Baroque, Rococo, and Secessionist buildings literally have depicted grown form, while biomorphic design advances discussions of biological form in architecture, and biomimetic design imitates both form and processes from nature. And so there's a kind of variety of ways in which architects and designers have engaged with some of these topics to sort of varying levels of depth and sort of aesthetic or other kinds of interests. More recently, Neri Oxman's mediated matter group has gone as far as using silkworms as construction workers in the creation of the silk pavilion seen on the left, and David Benjamin's MoMA PS1 pavilion Hi-Fi put the potential of mycelium as an architectural component on an international stage through its display at MoMA PS1 in Brooklyn. The acquisition of this practice called The Living by Autodesk a couple years back demonstrates industry interest in such developments and sort of new ways of looking at and utilizing biological materials.
Finally, we see even Rem Koolhaas, the famed urbanist, has turned towards the kind of technologies and species of the countryside as a kind of new architectural frontier. Our work moves beyond biomimicry and introduces bioagency as a design strategy, leveraging digital feedback to transform traditional design authorship into a mediation between biology, technology, and human intention. Bioagency liberates designers from an anthropogenic paradigm, subverting the primacy of humans over nature, proposes a new system for assigning value, and promises potentials for symbiosis with nature. It willingly synthesizes the intentions of the designer with natural processes. And so here we start to kind of put this new approach or term or kind of value set in dialogue with some existing and strong approaches that have dealt heavily with the kind of intelligence of biological material and suggest kind of new ways of advancing the kind of biological paradigm in architecture. And so next we'll kind of chart some practices that we see engaging with these kind of processes and strategies.
And so these graphs sort of map from left to right, an interest in materials and processes versus an interest more primarily in visualization and form, and sort of vertically map from lab or sort of research interest to maybe a more practice or industry sort of application side of things. And so we see there's a bunch of sort of actors in this space working, again, sort of all across the spectrum, a couple of projects from which we saw previously. But we're interested, again, in the kind of materials and processes side of this spectrum where we're locating this bioagency process. And so while some of the kind of aesthetic qualities of the sort of grown materials come through in that work, the interest is not primarily in kind of mimicking biological form, and any sort of aesthetic qualities that come from that work is sort of a process of sort of actually using that form literally and sort of drawing qualities from it to inform the construction of larger wholes or architectural assemblies.
So next we'll look at some terms that I think are kind of important in evaluating the kind of digital fabrication lexicon or history. And so we start with some of the kind of major terms defined by Lisa Iwamoto in her book, Digital Fabrications, which kind of catalog the early approaches to digital fabrication, many of which are subtractive in nature. And then two more recent developments, Adam Freer's digital materialurgy, which is more interested in the kind of unpredictable qualities of matter, And then Mario Carpo's form searching, in which structural optimization through computation allows for new relationships with material, because the kind of process of engineering no longer starts at tables, but it might start with the kind of forms and material itself. We're also interested in kind of questions of what is standard, what is maybe non-standard, and what is standardless. In particular, in relationship to biological materials, in which things like wood are highly codified, but other kind of promising materials are limited in their kind of coverage in code, or coverage at all.
And so we're interested in thinking about what is this, what is the kind of workflow, we can say, like from forest or from site of growing through a kind of like industrial process of standardization, in this case, maybe the production of plywood, for instance, that takes that sort of grown variable form and translates it into a sort of uniform thickness, predictable sheet material that has knowable qualities and structural performance and other sort of performance characteristics. And so traditionally, that material has then been sort of milled through subtractive processes to create a kind of irregular form from that standard material. And so we're asking in a lot of this work, what would these modes of digital fabrication look like using new sort of visioning technologies if we apply that to standardless materials, or materials that might kind of resist a standardization similar to the production of plywood or dimensional lumber? And so in this case, that involves sort of scanning and kind of understanding that material, and then allowing those qualities that are understood computationally through sort of understanding the form and structural properties of these different materials, and allowing that to influence the kind of formal qualities or other sort of performative or aesthetic characteristics in the built construction, and allowing that process to sort of shape the end product along the way through the design process. And so the first, we're going to start shifting into some teaching and research work by us now. And so in talking about some examples of biological agency, the first category here we're calling digital doppelgangers, which really relies on this visioning and the creation of a digital twin to kind of inform the process and help us to understand the material through sort of various means. And so this first project, called Retooling Bamboo, is part of a longer research initiative in collaboration with a couple of faculty at Virginia Tech, including Jonas Hauptmann and Daniel Heinemann. So the interest in this project in using bamboo is kind of started out a little bit thinking about this kind of cultural aesthetic stigma that exists around bamboo and some other sorts of natural materials. If you think of anything kind of aside from lumber, then there's various associations of this material with sort of informal or temporary structures, such as bamboo scaffolding, which has sort of incredible utility and structural capabilities, as is like well known in Asia and other parts of the world. And we're also contending with the likes of the cultural imagination in terms of Gilligan's Island and the sort of sequestering of bamboo as a construction material to this kind of like tiki hut kitsch. And those are sort of barriers that need to be overcome if the material is to be kind of implemented on a wider scale or within other cultural contexts globally. And so this work started by looking at a kind of analog process of analyzing the material by sort of systematically cutting sections, scanning that material in kind of a 2D scanner, drawing profiles from those cut sections to kind of analyze what the sort of general parameters were for how this bamboo grows from top to bottom, and sort of the wall thickness decreases as the overall diameter decreases, going from right to left here up this bamboo pole. And we're working with a particular species of bamboo here native to Vietnam. It's a tropical species, so it's very sort of solid compared to a lot of other types of bamboo. And so that sort of wall thickness allows us to do some things later on in the project that are maybe more specific to this kind of category of bamboos, as opposed to some of the more commonly seen thin wall varieties. So the next step was to kind of bring computation into this and sort of automate part of that process. And so as maybe some of you know, thanks to Lizzie Needham for her work on this project recently in January, we're looking at developing a sort of 3D scanning system, which has become quite robust now, that basically uses 3 photographs of the material at different rotations to construct a relatively accurate 3-dimensional model of the surface. And part of the ambition in creating our own kind of 3D scanning method here was to kind of democratize that step of the process. And so instead of relying on very expensive and elaborate sort of pre-made 3D scanning machines and software, this is very relatively low data and really easy to implement with very little technology and very little cost. So in taking that computational understanding of the material, you'll see a couple sort of drawings like this, like these kind of system diagrams in the upcoming work. And we're basically using this as a kind of demonstration of the workflow. So it sort of is aligned roughly with time in the project, going from left to right across the screen. And these different rows sort of categorize the different sort of actors in this process. So on the top, we have the user or the designer. In the middle, we have sort of an understanding of the material. And on the bottom, we have this autonomous system or the computational understanding of that material. And so there's this process in which a kind of overall assembly is developed and proposed by the designer. Meanwhile, the material is sort of scanned and inventoried and compared to a sort of range of possible joints in the overall assembly. And then there's this sort of adaptation as those parts are sort of milled and fed into the completing pieces for the assembly. There's an adaptation and a bit of feedback, as you can see in the line on the top of the screen, where the overall assembly is adapted a little bit based on the sort of range of potentials informed sort of or programmed by the material inputs to the system. And so that might be a little bit abstract here, but in another drawing, we can see there's an idea about having some sort of idealized form developed by the designer on the top. And if you start allowing that kind of structure or that assembly to adapt with longer, in this case, longer or shorter materials inputs that are based on the kind of node spacing of that material, given that it's sort of solid at each of those nodes as the bamboo is growing, the structure is allowed to kind of adapt itself based on those material inputs. And so these are the kind of ideas behind the project. And here are some images of initial sort of milling tests, developing some joinery methods here. You can see how, in this case, the kind of facing of the material allows us to reveal the kind of grain of it. So it's sort of read a little bit more along the lines of a live edge timber, as opposed to what we might more traditionally think of as like a bamboo material. So starting to try to question some of those preconceived cultural associations with bamboo, and stay tuned for upcoming photos of some assemblies built with this, both at Virginia Tech with our collaborators and here at UVA this semester. Another project dealing with this idea of digital doppelgangers we call Twinned Assemblage. And the results of this work shown in this section of the talk are from a course that we taught together last year at the University of Tennessee, Knoxville. And so the process is a little bit similar in that we're using sort of very low, relatively low technology, accessible, democratized 3D scanning solutions. But in this case, instead of building that from scratch, we're using a 3D scanning smartphone app that kind of runs on anyone's sort of smartphone today. And it's a photogrammetry method that sort of digitizes this material and produces a 3D scanned mesh together with the photographic image of the material mapped onto the surface. And so students were asked to create digital inventories of a variety of materials. Some of them were sort of biological materials, like the pine cones you see on the bottom. Others were geological or some hybrid of the two. And there was this process where those sort of digital inventories were then used to create through a variety of aggregation methods and digital simulations, kind of an idea about an assembly of these objects. And one of the important steps in this process was this idea of a distillation of those digital meshes, whereby we manipulate this sort of digital information to extract certain qualities that can inform particular assembly strategies. And so in the second row here, you can see these kind of coal fragments were scanned and then intentionally reduced to a very low polygon mesh in order to identify the largest flat faces, which then became a sort of interface between different pieces in this kind of spring simulation that created these sort of curving and arcing forms. Again, the system diagrams is a really important tool here to choreograph this relationship between design, computation, material, and also fabrication. And there's always an idea about how the 3D scans and the quality from the material that's understood computationally informs or provides feedback for a kind of aggregation method. And so in some cases, the sort of exact qualities of the final aggregation are not predetermined by the designer. There's a kind of more general idea about that. And then the exact qualities are a collaboration between the designer, the design intent, and the physical material as it's understood through this technological workflow. This one was using a kind of gravity simulation to pack these objects into a sort of predetermined form. And there's a variety of different methods here. Again, thinking about that distillation method, there's a bunch of different ways that we can think about this material, taking on kind of different qualities or having sort of distilling or extracting different elements that can be used strategically by the designer in order to determine what qualities of the material are most important to inform a particular aggregation.
So these kind of scrappy studies on how we create like kind of digital twins, or what we've been calling in the last kind of, in these three examples, digital doppelgangers, are really aimed at how our kind of digital understanding of material can not only kind of duplicate reality, but distill it and leverage its qualities. And so this project that we'll show now is a design build project that came out of a studio that we taught together at the University of Tennessee, where the students attempted to reconcile these kind of branches with a design form here represented as the kind of curve. So how could the kind of peculiarities of the branches achieve what the kind of curve set out to do? And so again, the system diagram becomes an important actor for us between the kind of biological and the designer, a kind of relationship in which there's kind of feedback and conversation before a kind of final output. The process is not always linear. And so in this case, the students were looking at how branch curvature could be kind of documented and analyzed through computational means. So first starting with the kind of 3D scanning on the smartphone, a really kind of simple, cheap way to do it that didn't require high-tech equipment, and then starting to pull out different pieces of information that could be then kind of put into the recipe for the design.
There's also an idea about sort of, again, having some kind of predetermined idea about the assembly. And so in this case, it was a simple sort of wall structure with a kind of curving base and a straight top. And so the complex geometry of that surface was sort of broken down into a series of sort of legs or elements through manipulating that mesh. And then there was an idea about mapping these materials that were 3D scanned to that surface. And so on the bottom middle, you can see they're sorted from larger diameter pieces arranged along the bottom to smaller diameter pieces along the top. But there's also a kind of mapping of the overall curvature of each branch to a particular part of that surface, matching the sort of curvature of the idealized surface. And there's a bit of feedback where the curvature of those branches, if it was very different from any possible location on the mesh, can actually inform and distort the overall geometry of the project, allowing the material to feed back and influence the final form. Here you see some sort of steps in the process. This was a project by 2 students done in the course of a semester, and they used the Bradford pear, a kind of invasive species, as the source material for the project. And they also had an idea about programming the overall geometry into each of these nodes, which they generated through a series of grasshopper scripts. And so there was no need for any sort of large scale scaffolding or templating in order to assemble this structure based on the kind of end angle of each of the branches together with the program geometry in these joints. The structure kind of self self-assembled itself as long as everything was kind of inventoried and put in the right place in the right rotation.
The final images of the installation show a kind of relationship between the constructed joint and the raw material, the Bradford pear branches, which kind of naturally break off of this invasive plant species, and some kind of relationships or kind of a simpatico with even the bird that decides to sit on it.
There's an idea as well that this, the sort of exact qualities of this version of the installation is determined by that Bradford pear tree, but if a different species were chosen with different sort of irregularities and qualities to its branches, then the installation would take on a totally different quality as those material inputs are taken into that system and create their own sort of set of adaptations and sort of twists and turns within the structure.
So the second approach under the umbrella of biological agency is growing. And so with the growing projects, we're looking at how the growth of organic material can be scaffolded by human intention. So in these examples, starting with a mold designed by the designer, and then having that interact with a live system, in this case, hydroponically grown barley seed. And so we started to kind of generate a series of models of potential kind of buildings or walls, and trying to think about how a kind of grown architecture might take on new qualities in terms of enclosure, light, threshold, and what kind of forms the kind of live condition would respond to, seeing a kind of grid on the left versus an undulating surface on the right, and seeing some of the kind of ways that the live system plays into these molds.
And in these examples, we're also using sort of collaborating with the barley and using it as a kind of aggregator or an adhesive method. And so you can see there's also some other kind of natural fibers embedded within these panels, but in these cases, there's no adhesive used. It's sort of bound together entirely by the plants as they're growing.
So we recently attempted to scale this technique up now to the scale of the furniture, thinking about maybe kind of traditional furniture fabrication processes such as woodworking and how they might intersect with these kind of processes of growing.
And so the kind of methods used here, you can see on the left, a kind of view of the bottom of this mold, right sort of before it was harvested. And in using kind of these methods to collaborate with these natural entities or biological entities to create a kind of grown form, in this case, a chair, the process maybe has more in common with the production of fodder for livestock than it does with any other sort of furniture production technique or fabrication method. And so here we see some images of this first prototype that's a kind of utilizing all of these methods. And there's sort of no adhesives or any other sort of matter used for the top half of this piece of furniture, except for the barley itself that's kind of manipulated as the seeds are grown in order to interweave these roots and produce the form that you see here.
So the final category of projects we'll put forward after kind of digital doppelgangers, growing, is this kind of final category of forming. And so we'll start with a machine that we developed during our fellowship at the University of Tennessee, which takes the kind of process of using an inflatable mold to inform an additive fabrication process rather than a subtractive fabrication process.
And so in this case, thinking back to some of the earlier parts of the talk where we're kind of critiquing or transforming, well, traditional digital fabrication methods. If we think about the sort of fabrication of sort of curving surfaces, they might involve the milling of a bunch of plywood or other sheet material to make a kind of waffle grid of these curving forms that's then skinned in some way. They might involve using milling and subtractive methods to sort of create these complex curvatures in large blocks of foam, which produces a lot of material waste. And because those additive and subtractive processes are sort of removing a lot of material and then program just that one specific geometry into the material or into the mold, you have to kind of make a bunch of those every time you create a new form. And so in this case, we're using pneumatic technologies to basically build a mold that's manipulative and reconfigurable using a grid of these inflatable pillows. And so we can see here some details of this machine, sort of powered by Arduino and sort of informed or programmed directly from Grasshopper and Rhinoceros. So there's a very sort of maybe DIY approach to this, but again, it's very low technology, democratized, and not really using a lot of highly specialized knowledge. And you can see the kind of grid of pillows in the foreground are attached together on the top and bottom. And so by inflating each pillow to a certain amount, we can program a certain geometry and curvature into the top of that surface and then use it as the surface upon which we can cast a variety of different materials. And here you see kind of the first prototype of this system, which is a sort of forming machine measuring 3 feet by 10 feet. Using a grid of these 1 foot cubic pillows that again can be sort of inflated and then air can be vacuumed out to reset the system and then inflated again for the next mold. And so it's both can be used highly repetitively to produce the same form again and again, but it can also be used to create a different form every time with sort of no material waste, as it's a kind of malleable system, not relying on sort of subtraction or addition in the production of these molds. And so in thinking about how to apply this technology, we're going to talk about our installation Homegrown, which Matthew mentioned at the beginning in our introduction.
So specifically, this project was the culmination of our fellowship at the University of Tennessee, and the work draws from Tennessee's iconic landscape of invasive plants, as well as from landscape maintenance waste and forestry activities. And I guess this kind of site isn't so unfamiliar up here in Virginia either, we've kind of quickly found. So Homegrown is seen here on display at Knoxville's Museum of Art's South Garden between the stepping pink Tennessee marble facade designed by Edward Larrabee Barnes and the historic brick elevation of the neighboring factory turned condominium building. The installation's 4 walls form an exterior room within the larger walled garden. A series of volumes are subtracted from the walls to create openings that serve as doorways and windows.
So here's a diagram sort of that pillow forming process, what's going on sort of computationally on the design side of things before sort of the code is sent to the Arduino powered machine. And essentially we're sort of analyzing this surface and averaging a series of heights in order to essentially determine a kind of inflation time value to change this geometry from a kind of digital understanding of the surface to a kind of physical representation or manifestation of that surface using the previously seen pillow forming machine. And in this case, there's a series of 4 walls, some of which are taller than 3 feet, and so involved a kind of 2-step forming process for the top and bottom of each of those surfaces.
The resulting installation proposes an alternative material ethic by making use of small-scale landscaping waste, including invasive plant species such as kudzu, bamboo, and various tree species, as well as forestry waste. The plant fibers are formed into lightweight wall-scale panels using a liquid bio-based binder. In a nod to the materials of traditional American framing, the panels are faced in pine needles and rest on a base of dimensional lumber. The top edge steps up and down, suggesting doorways, windows, ledges, seats, a rewilding of the domestic. The resulting architecture is not flat and hard, but fuzzy, fluffy, furry, shaggy. It is simultaneously primitive and high tech, and it is not permanent, but temporal. So this kind of architecture may require kind of caretaking and maintenance, not unlike a landscape or an occupant. Homegrown is seen alternatively as a ruin or as a topiary hedge. Viewed as a whole, the work begs a question of how our buildings are made, the materials with which they are made, and the new potentials that might be unveiled if these established systems and societal expectations can be reimagined.
Here we see in the last couple of images, again, the sort of flat exterior of these surfaces versus the kind of undulating, more natural interior, and the contrast between those two as you look into and out from the structure. Thanks so much for listening to our talk today. I hope we can maybe answer some questions you might have about the work that brings together new technologies and democratized technologies to essentially maybe more intelligently utilize the kind of embodied intelligence of natural materials in built form. Thanks.
Great, thank you, Kyle and Katie. It's always difficult to do the round of applause, but you can just imagine it. There you go, and someone's got his hand up. That's clapping, right? Not a hand for a question?
Yeah.
Yeah, I guess let's open it up to questions first. Well, while they're, oh, and someone? Or did he just freeze? No, he's there. While everyone's thinking about their questions, I'll go ahead and pose one. I mean, yeah, a wonderful breadth of work, and it's really great to see and kind of think about how this relates to landscape. So in a lot of ways, obviously my question is quite sort of prejudiced from a landscape position. I got particularly excited when you were speaking about growth, right? And sort of this idea of kind of change over time, and how the medium that you're kind of working with isn't purely a sort of result of a biological process, a sort of standardless biological process, but it actually has potential for new form and new mass, new volume, etc. And so I'm kind of wondering how you might think of that in relation to your systems diagrams, where there is some feedback, but I just wonder if by sort of essentially multiplying that indeterminacy of new, like emerging form, how might the sort of system diagram be kind of reconceived, whether it's branching scenarios or something similar?
Yeah, well, I guess I think that the system diagram is meant to anticipate that there might be kind of multiple scenarios or even failures, but I think kind of branching scenarios is definitely something that would come into it. And we're really interested in how Mario Carpo talks about structures today, which I think is still quite radical and maybe not fully accepted by the engineering community. But the idea that you can kind of like run multiple simulations and that there's multiple right answers rather than a kind of top-down approach is really exciting. And so one of the questions that I think we're facing, particularly when you get into things like growing, are the kind of measurability of some of these materials when it comes to kind of structural applications. And so in that way, I see the kind of like multiple scenario system diagram as being something that could start to confront those challenges. If the growing medium grows optimally, maybe it has this branch, but if it fails because of certain conditions, maybe it goes down this branch, and then other systems have to kind of multiply to pull the weight. So yeah, I think it's a really interesting question.
Yeah, and that's something that we're exploring in kind of maybe the next versions of that homegrown installation, which is basically using more digital modeling and topological optimization to program structure into that material, where it can kind of become thicker in certain places where that's kind of needed for structural purposes or for like sculpted furniture integrated into the surface. And it could also become thinner in other places where that sort of structure isn't needed or where openings need to be created. And so I think we need to consider ways that can be adapted into those system diagrams, which right now are maybe you're kind of seeing the kind of maybe final version that's associated with the built version of each of these projects that we shared. But those are really intended as working documents that are a way for you as the kind of designer or choreographer of this process to sort of think about the relationships and interdependencies between these different actors.
It could be interesting to sort of, I'm not telling you guys what to do, obviously.
No, please.
It could be interesting to see that diagram, yeah, less as sort of this final form of the diagram that's related to the final form of the project, like you're talking about. But yeah, something more of a series that just sort of describes the kind of the dynamism of the choices made and where things were potentially ran into a dead end and then you went down another path. But to kind of see that as a larger sort of sequence of drawings that tells that narrative of indeterminacy, bioagency, agency of the designer, etc. Would be really fascinating.
Yeah. In that sense, where it almost gets into like a sort of like decision tree, right? Sort of like mapping all the different possibilities as you kind of like branch and progress along the way.
Mm-hmm, mm-hmm. Any other questions? In Selma?
I don't know that I mean, I have many thoughts. Great talk, Katie and Kyle. It really raises a number of issues in regard to the agency of the designer and the extent to which authorship might, where is it not only valued, but where is it actually evidenced more in the work, you know, whether it's about putting in place these actors, whether they be the technology, the material itself. I was struck by the context, the sites of these of these interventions, which themselves are highly nurturing in and of themselves. So this is sort of kind of really careful and thoughtful curation of this kind of process that emerges ultimately. I guess my question is more in regard to this notion of authorship and where do you find yourselves being most not only effective in a pragmatic sense, but most willful in the way that, right, the design is evolving and ultimately manifests itself, right? Because this is kind of, on the one hand, a democratization of technology and also of the designer, right, as sole author or partners authors is one thing, but then ultimately you are, right?
Yeah.
Your will is in your authorship is imposed on the work.
Yeah, no, I think it's a important question because there's kind of two layers of authorship that you suggested, and one is like the systems themselves or the technologies, right? And in a way, those are what we've been trying to kind of develop or refine, like the kind of twinning, growing, forming, like that those could be kind of set up and put in place, and then there would be a second level of design authorship, right, where someone else, another designer, could come into the system and manipulate things accordingly, or in the cases of like the experiments that we've carried out, that we again exercise authorship that second time. So certainly I think the designer remains present in this process, and actually maybe they're in those two places, like has two very big but actually very different roles. I think something that's been interesting for us as we develop the work is to start to think about, instead of us having kind of preferences to certain forms or there's kind of certain spatial logics, that we start to say, okay, what does the material have in terms of preferences and how could those be harnessed? Or like maybe those things have always been there, but it's been difficult for us to harness them because of the tools we've been working with. And so, then we come in as curators to the material, right, with something like the branches, and we say, okay, we think the center lines are really important, or we think the curvature is really important, or the diameter is kind of implicitly important because it suggests different structural qualities. If you have a larger member, you have kind of different structural qualities than a smaller member. So I think some of the things are suggested, but there's still a huge amount of curation. And in that way, there is a kind of added layer to the designer as curator, kind of curator of the natural qualities. Does that seem fair, Kyle?
Yeah, I think that's great. I mean, yeah, we're basically thinking about there's kind of the front end and the back end of any one of these projects. And so on the front end, we're kind of inventing those technologies, whether it's the pillow forming machine or the kind of like customized 3D scanning process for bamboo. And in that sense, it's maybe taking back some more authorship for the designer, as opposed to, I don't know, if you think about kind of every kind of tool or software that we use has a bunch of sort of capabilities and limitations that can more or less influence a process, some more than others. So if we think about like Revit and BIM, there might be more influence coming from sort of like the building products industry and codes and standards that are maybe sort of forcing a design one way or another, maybe removing some authorship from your agency as the designer. And so we're sort of trying to develop these tools that then you sort of have leeway to sort of, manipulate your own sort of authorship or mark on the material in that sense. And so I think on the back end, there's, like Katie's suggesting, maybe room for some more willful interpretations or applications of these technologies. And I think we're just getting to the point now where some of these things are more robust, where they could be kind of handed off to others or used sort of, whether it's within the school through coursework or research projects or whatnot, to kind of see how much leeway there actually is in terms of like a breadth of possibilities for any one design that relates to this sort of your opportunities for authorship in using and applying those methods and technologies, if that makes sense.
It does. My reaction to your comments, to your response would be, I think that your sensibilities can be found or traced at the very preparatory stages of the way you might bring the tools together and systematize those process protocols really. And the sensibility then kicks back in at the back end, right, where you are coming back in and introducing really a consistent language, I would say, in the way that the material is curated, modified, formed, so that I'm interested in those traces or the extent to which those are evident at various moments of the work, which is great.
Thanks.
Yeah, I think your question raises for me also like the idea of how the designer authors or takes back authorship from the building supply chain kind of industry, right? So oftentimes we're forced to certain things because of our material palettes and budgets. So
and the higher paid consultants potentially.
Yeah. Exactly. Yeah. So I think there's like territory to be gained there for architects.
Maybe one last question.
Matthew, I have a question.
Yeah, go for it.
Kyle and Katie, I wonder if you could speak to your position on fabrication, design research, as it relates to moving forward academic pursuits and academic sort of knowledge held by an academy versus how it might influence an industry, and how you think about either the Bamboo project as having a duality, a position there, or if you think it's appropriate or valuable for projects to move, position themselves explicitly in industrial innovation or construction practice innovation. What are the pluses and minuses, and how do you see your work sitting inside of those two priorities?
Yeah, it's a really good question. I mean, I think we see a lot of opportunity for developing this sort of novel work, or maybe, I don't know, in some ways more like fundamental ways of thinking about technology and like developing these different methods that we've been talking about. We see a lot of opportunity for that happening kind of within the academic space, right, through design research and through teaching. And so that kind of like academic world is like in some cases sort of gives you an alibi in some ways to like develop this type of work that might be may be more difficult and sometimes, or have different sorts of limitations due to kind of like the forces of industry and working in the profession. But we're definitely interested in looking at how the work can sort of not just exist within academia, but can kind of get out into the world. And so in some ways that's happened. We've got some like popular press attention through the work done at the University of Tennessee, which has been super interesting to see like what journalism is interested in and getting it out to the public. But we're also interested in the future looking at more at how we can start to work with different industries to incorporate some of these techniques. And that's happened, I know, at other schools like University of Michigan and MIT have great relationships with some kind of like stone manufacturers to do sort of really novel applied research in those areas that's sort of using industrial workflows. And I think there's a lot of opportunities to work with forestry, and that's kind of been using all these scanning and visualization methods for decades now. And there's a kind of break between that information that's just used to produce a standardized piece of lumber, and then it's sort of that data is erased. But if that data could be harnessed and used, kind of attached to that material, and could create a linkage between that understanding of the material as the kind of raw tree and connect it to like the design end of things, then I think there's going to be a lot of interesting potentials for like these kinds of ideas about bioagency and how those forms could influence the built environment. I don't know if that answered your question. Just a couple, some of many thoughts.
Yeah, great.
Wonderful. Well, thank you again, Kyle and Katie. Really amazing work. And I look forward to seeing you guys out at Milton.
Us too. We're looking forward to starting to work out there, and very excited about what you're all doing out there as the Land Lab. So thanks for the invitation.
Yeah, thanks so much.